Imagine for a moment stepping into a bustling server room, that low hum of countless machines processing our digital world. Or picturing a vast industrial facility, all its intricate machinery running in perfect, synchronized motion.
Yeah, complex places.
What you might not immediately consider are the unseen protectors, those silent guardians, meticulously engineered to prevent catastrophe if fire were to erupt.
Absolutely. Often overlooked.
And often, these protectors wield a gas you're incredibly familiar with, carbon dioxide.
That's right, CO2.
Yes, that very same CO2 that adds the delightful fizz to your soda plays a remarkably critical life-saving role in sophisticated fire suppression systems.
It really does. Quite versatile.
Today, we're taking a deep dive, a true shortcut to being exceptionally well-informed about one of these vital unseen guardians. The Standard on Carbon Dioxide Extinguishing Systems.
NFPA 12.
We're focusing on the comprehensive 2022 edition of NFPA 12. Our mission is to extract the most important nuggets of knowledge, the surprising facts, and the crucial safety insights from this foundational document just for you.
That's right. Our goal isn't just to list facts. For you, the curious learner, we want to help you quickly grasp the why behind these powerful CO2 fire suppression systems.
With reasoning.
Exactly. Why are they designed with such meticulous detail? Why are the safety protocols so incredibly stringent? We'll journey through the essential principles and critical considerations, ensuring those aha moments without the information overload that often comes with dense technical standards.
Yeah, cutting through the jargon. And as a quick, fascinating tidbit from the very first page of our source material, you know you're dealing with a truly global, comprehensive standard when its abstract begins in Farsi.
That is interesting. Shows the reach.
It highlights how widely the National Fire Protection Association, or NFPA, translates and makes its standards available for download across the globe.
A global leader in safety.
But don't worry, we're immediately diving into the wealth of information provided in English for our deep dive today. Okay, let's really unpack this. Before we get too deep into NFPA 12 itself, we need to understand the bedrock it stands on. The National Fire Protection Association.
The NFPA, yeah.
What exactly is the NFPA, and why are their standards, like NFPA 12, so incredibly important and influential in the world of safety?
If we connect this to the bigger picture, the National Fire Protection Association, or NFPA, is a global powerhouse dedicated to eliminating death, injury, property, economic loss caused by fire, electrical, and related hazards.
That's a huge mission.
It is, and they achieve this primarily by developing and publishing over 300 consensus codes and standards.
Consensus-based, that's key.
Exactly. What's truly remarkable about NFPA standards, like the NFPA 12 we're discussing, is the rigorous consensus-based development process. It's not a top-down mandate. It brings together hundreds of volunteers.
Volunteers, wow.
Yes. Engineers, industry experts, fire service personnel, manufacturers, and even end users, all collaborating to achieve consensus on complex fire and safety issues.
So, diverse perspectives.
That collective expertise, spanning diverse viewpoints, is what gives these standards their immense authority. It's crucial to understand, though, that while NFPA administers this process and sets rules to ensure fairness, they don't independently test or verify the information.
Ah, okay, so they manage the process.
Right. The power comes from the peer-reviewed knowledge and experience of those dedicated volunteers.
That collaborative, consensus-driven approach sounds incredibly robust. But it's also striking that the standard itself comes with some very explicit, important notices and disclaimers.
The legal side.
It essentially states that the NFPA disclaims liability for any damages from relying on the standards. That feels like a significant point about personal responsibility, doesn't it?
It really does.
It's telling you, the user, that you must rely on your own independent judgment or seek competent professional advice, and they don't guarantee the accuracy or completeness.
Precisely. That disclaimer isn't just legal boilerplate. It's a fundamental statement about how these standards are meant to be applied.
Right.
While they provide best practices and guidelines developed by experts, the ultimate responsibility for their correct implementation and for ensuring safety on a specific site rests with the user and qualified professionals.
So use your judgment.
It's a very practical aspect of safety engineering. And this brings us to an even broader implication. NFPA standards are not merely suggestions.
Okay.
They are copyrighted documents made available for wide public and private uses, but critically, they are very often adopted by reference into laws and regulations.
Oh, so they become law.
Essentially, yes. This means that specific portions of NFPA 12 or the entire document can literally become part of the legal framework governing fire safety at federal, state, or local levels.
Wow.
When adopted by reference, authorities usually just cite the title, edition, and publishing information with any desired deletions, additions, or changes noted separately. This intertwining of privately developed expertise with public legal enforcement is what truly underscores the incredible influence and importance of these documents.
The history of NFPA 12 itself speaks volumes about this continuous evolution of safety science. Can you believe work on this standard actually began way back in 1928?
1928, that's incredible, almost a century.
And it was first adopted in 1929. Since then, it's been revised countless times over the decades, 1933, 1939, 1940, and then multiple times through the 40s, 50s, 60s, and all the way up to this 2022 edition we're diving into today.
Constant refinement.
That's nearly a century of continuous refinement. What does that tell us about the nature of fire safety?
It demonstrates that fire safety is never a static target. It's a constantly evolving field, always adapting to new experiences, new research into fire dynamics, and new technological advancements.
Always learning.
Exactly. The fact that it's prepared by a highly specialized group, the Technical Committee on Gaseous Fire Extinguishing Systems, means that the document is being meticulously updated by experts who live and breathe this specific area of fire protection.
The real specialists.
They're integrating lessons learned from real-world incidents, new scientific understanding of how gases interact with fire, and the development of safer, more efficient equipment. It's a living document, ensuring our silent protectors are always at the cutting edge.
So, with that essential foundation laid, let's finally get into the star of our show, carbon dioxide.
CO2 itself.
What is CO2 as a fire suppressant, and how does it actually work its magic to put out a blaze?
What's fascinating here are the inherent properties of carbon dioxide that make it such a formidable fire extinguishing agent. First, it's a colorless, odorless, electrically non-conductive, and inert gas.
Inert, non-conductive key properties.
Very key. This means it won't add fuel to the fire, conduct dangerous electricity, or leave behind any unpleasant smells or residues after discharge, a huge benefit for sensitive equipment.
No cleanup, basically.
Pretty much. It's also approximately 1.5 times heavier than air, which is a key physical property for its distribution.
Okay, so it settles.
It tends to displace air downwards, yes. Its primary mechanism of action is incredibly effective. It extinguishes fire by rapidly reducing the oxygen concentration, the vapor phase of the fuel, or both.
Smothering it.
To the point where sustained combustion simply cannot occur. When liquid CO2 is discharged under pressure, a large portion of it instantly flashes into vapor.
Flashes to vapor. Oh,
And a significant part converts into finely divided dry ice, a sort of snow, at an astonishingly cold -109.3 degrees Fahrenheit. That's minus 79 Celsius.
Wow, that's freezing. Dry ice snow.
Exactly. This rapid expansion and extreme cooling also cause water vapor from the entrained air to condense, which creates that characteristic white cloud you might have seen in videos.
Right, the big white cloud.
Yeah.
So it's essentially suffocating the fire by stripping away its oxygen and also providing a significant cooling effect.
Precisely.
That sounds like a powerful 1-2 punch. What are some of the other significant advantages, the pros, of using CO2 systems? Why choose CO2 over other agents?
Well, the benefits are indeed substantial for specific applications. Firstly, it's non-corrosive and non-damaging to most materials, leaving absolutely no residue behind.
We mentioned the no cleanup. That's huge for electronics.
It's a massive advantage in environments with sensitive equipment like electronics, machinery, or priceless artifacts. Imagine a fire in a data center. Using water would be disastrous.
Loss.
Right. But CO2 cleans up, or rather disappears without a trace, drastically reducing downtime and cleanup costs. Secondly, carbon dioxide provides its own pressure for discharge,
Self-pressurizing.
which simplifies system design because you don't need separate pumps or complex pressurization systems, which means fewer points of failure and easier installation.
Makes sense.
Because it's a gas, it can penetrate and spread efficiently to all parts of an enclosed hazard, reaching nooks and crannies that other agents might miss.
Gets everywhere.
And, as you mentioned, its electrically non-conductive nature makes it perfectly safe for use on energized electrical hazards,
Critical for power facilities.
which is a major advantage in places like power substations or high-voltage switchgear rooms where maintaining power is crucial or where water could pose electrocution risks.
That's a compelling list of advantages. But here's where it gets really interesting and critically important. Despite all those pros, CO2 is far from a universal fire solution.
No, definitely not.
It has crucial cons or limitations. When shouldn't you use CO2, and why is understanding these limitations just as important as knowing its strengths?
This raises an important question. Knowing CO2's strengths, what are its specific weaknesses? The standard is incredibly clear here.
Okay.
CO2 is explicitly not effective and should not be used for fires involving certain types of materials. This includes chemicals that contain their own oxygen supply, like cellulose nitrate.
Right, things that burn without air.
Exactly. They can burn even in the absence of atmospheric oxygen. It also applies to reactive metals such as sodium, potassium, magnesium, titanium, and zirconium, as well as metal hydrides.
Reactive metals. Okay, why not?
The reason is fundamental. These materials either don't rely on atmospheric oxygen for combustion, or they react in ways that CO2 simply cannot suppress.
So it just doesn't work on them.
It doesn't. However, there's a crucial nuance. While CO2 doesn't extinguish these specific fires, the standard notes it does not react dangerously with these materials or increase their burning rate.
Oh, that's interesting. It doesn't make it worse.
Right. In fact, in total flooding systems, CO2 can still protect adjacent ordinary combustibles or be used if these reactive metals are already covered by another material, like sodium stored under kerosene.
So it can protect around them.
It can. But for local application systems, which use a high-velocity directed discharge, it's especially important to avoid direct application onto these reactive materials, as the force could potentially spread them or exacerbate the situation.
Got it. Don't blast the burning metal.
Basically, yes.
Yep.
So it's not just about what it can put out, but what it can't affect or even inadvertently harm.
That's a vital distinction. And speaking of precision, it's not just any CO2 that goes into these sophisticated systems, is it? There are surprisingly strict quality standards for the extinguishing agent itself.
Absolutely. Purity matters.
What are they, and why does that level of purity matter?
Absolutely. The standard specifies very precise quality requirements for the carbon dioxide used. For instance, the vapor phase must be at least 99.5% carbon dioxide.
And 99.5% pure.
With no detectable off-taste or odor. The water content of the liquid phase has to comply with a specific industrial standard, CGA G6.2.
CGA G6.2, okay.
Which is set by the Compressed Gas Association and outlines detailed purity levels for commercial carbon dioxide. Additionally, the oil content must not exceed 10 parts per million by weight.
Very low oil content. Why so strict?
These aren't just arbitrary numbers, they are critical. Impurities, such as excess water or oil, could significantly hinder the system's performance. Water could lead to corrosion within the piping, especially given the cryogenic temperatures, and oil could leave undesirable residues or even act as a fuel source itself.
Makes sense.
Yeah.
Don't want corrosion or more fuel.
Exactly. Maintaining this high purity ensures the agent remains effective and non-damaging. For this reason, the standard strongly recommends periodic analysis of the CO2 supply to ensure it consistently meets these strict quality benchmarks throughout its service life.
So regular testing of the gas itself.
Yes, to ensure it stays pure.
Here's where it gets really interesting, and for me, perhaps the most critically important aspect of today's deep dive. Personnel safety.
The absolute priority.
The standard emphasizes, quite starkly, that the most significant hazard of CO2 fire suppression systems is to human life.
It is. It's not the fire itself, but the agent.
This is where the engineering truly has to balance powerful fire suppression with incredibly meticulous protection for people.
What's fascinating here is that the inherent dangers of CO2 discharge at fire extinguishing concentrations are severe and multifaceted. The primary hazards are rapid suffocation.
Suffocation, number one.
Caused by the displacement of oxygen in the breathing atmosphere and significantly reduced visibility both during and immediately after the discharge.
Can't see, can't breathe.
Terrible combination. It makes rapid evacuation extremely difficult. Beyond the atmospheric threat, direct contact with the liquid CO2 or the dry ice snow that forms can cause severe frostbite due to its extremely low temperature.
Right, that minus 109 degrees Fahrenheit.
Exactly. The standard even notes that the discharge of liquid carbon dioxide can produce electrostatic charges, which, under certain conditions, could create a spark.
A spark from the CO2 itself.
Potentially, yes. So designers must account for these immediate and profound risks to human life, making human safety the paramount concern.
That's a huge aha moment for many people, realizing the direct danger beyond just the fire. So it makes absolute sense that there are extremely stringent restrictions, particularly for what the standard calls Normally occupied enclosures.
Yes, places where people usually are.
Let's unpack this. New total flooding CO2 systems, for instance, are generally not permitted in these spaces.
Generally prohibited, that's the rule.
What are the very specific exceptions to that rule, and what's the underlying reasoning for each?
This general prohibition is a cornerstone of the NFPA 12 standard, reflecting the extreme danger of CO2 in occupied areas. However, there are very specific, tightly controlled exceptions, each with a clear rationale.
Okay, what are they?
For example, total flooding systems are permitted when an inerting concentration is absolutely required and where alternative gaseous agents would either result in concentrations above their lowest observed adverse effect level, LOA,
Okay, the point where it becomes harmful.
Right, the lowest concentration at which adverse health effects are observed or would reduce oxygen levels below a critical 8%, posing their own significant risks.
So, if the alternatives are also dangerous in that specific situation.
Precisely. This means CO2 is chosen only when other, safer gaseous agents simply can't achieve the required fire suppression without creating unacceptable health risks.
Makes sense.
What else? Another exception is for fires involving energized electrical equipment greater than 400 volts in grouped electrical cables.
Why voltage again?
Especially where no gaseous alternative agent has been successfully tested to prove its effectiveness for such specialized high-voltage hazards. They're also permitted when current design methods or hardware for handling unenclosable openings or ensuring extended discharge aren't available for other gaseous agents.
So technical limitations of alternatives.
Leaving CO2 is the most practical choice. Marine cargo holds are another exception, as are marine engine rooms under conditions similar to the first point where an inerting concentration is needed, and alternatives raise LOAEL or oxygen concerns within the confined, unique environment of a ship.
Marine applications, right?
Each exception is a highly specific, justified scenario where CO2 remains the most viable, or in some cases, the only effective solution, but always with stringent compensatory safety measures.
And what about systems that were already there in those normally occupied spaces?
What's also critical is how existing systems are handled. For existing total flooding CO2 systems that are in normally occupied enclosures, they were only permitted to continue operation if they were retrofitted with specific safety features by December 31st, 2008.
A deadline. What features?
These mandatory retrofits included system lockout valves, pneumatic pre-discharge alarms, and pneumatic time delays.
Lockouts, alarms, delays. Got it.
The implication of adding new piping equipment, like these lockout valves and time delays, is significant. It increases the equivalent pipe length within the system.
More pipe changes the flow.
Exactly. This then requires the system's original flow calculations to be meticulously re-verified to ensure that the agent quantity and discharge rates are still sufficient to meet the design concentrations and discharge times despite the added resistance.
So you can't just add safety stuff without rechecking everything.
Absolutely not. This emphasizes how deeply integrated safety features are with the core system performance. You can't just bolt on a safety device without potentially affecting how the entire system functions.
Okay, so beyond those exceptions and retrofits, what are the general safeguards needed for any CO2 system to protect people?
To mitigate these inherent dangers, the standard outlines comprehensive safeguards that must be in place for any CO2 system, not just total flooding. For evacuation procedures, this means ensuring adequate aisleways and keeping exit routes clear at all times.
Clear paths out.
It also mandates necessary additional or emergency lighting and clear directional signs to ensure quick and safe evacuation in low visibility conditions.
Lighting and signs, crucial in that white cloud.
Absolutely. Exit doors from hazardous areas must be outward swinging, self-closing, and equipped with panic hardware, if lashed, to allow rapid, unhindered escape.
Panic bars, push outwards, standard stuff, but vital here.
When it comes to alarms and delayed discharge, the system is designed to provide alarms within the protected area immediately upon fire detection.
Immediate warning inside.
This is carefully synchronized with a delayed CO2 discharge and automatic door closures, allowing personnel sufficient time to evacuate before the gas is released.
Time delay is key.
Crucially, continuous alarms must sound at the entrances to these areas until the atmosphere is restored to normal and verified safe for entry.
Alarms outside, too, until it's safe.
Right. The pre-discharge alarms themselves must be highly effective, audible at a minimum of 90 dBA at 10 feet. That's about as loud as a lawnmower or a busy street.
Loud. No missing that.
And visible throughout the protected space, distinct from general building fire alarms. They must also be located within the enclosure, not just outside.
Inside, loud, visible, distinct. Got it.
The pre-discharge time delay must be of sufficient duration to allow personnel to evacuate from the remotest points within the space to the nearest exits, considering the fastest possible escape routes.
Long enough for everyone to get out. And here's where it gets really interesting and a bit provocative, considering the emphasis on delays. The standard actually allows for time delays to be omitted in certain occupiable hazard areas, like combustion gas turbines or engine test cells.
Yes, very high-risk, fast-fire areas.
These are environments where rapid-fire growth is an extreme risk, and even a brief delay in agent discharge could cause catastrophic damage or unacceptable safety risks.
The delay itself becomes a bigger hazard.
But if that time delay is skipped, the systems must be physically locked out anytime personnel are present in that protected area.
Absolutely locked out. No exceptions.
It's a stark but necessary trade-off. Extremely rapid suppression for critical equipment versus absolute, immediate human safety.
Indeed, that balance is critical and necessitates strict protocols. For identification and warning, the standard goes even further than simple signs. It recommends the addition of a distinctive odor to the carbon dioxide.
An odor, like adding scent to natural gas.
Exactly the same principle. Oil of wintergreen is a common, recognizable choice. The goal isn't just to make personnel aware of a fire, it's to help them recognize a hazardous atmosphere by smell if the system has discharged.
So you can smell the danger.
However, it notes this might be inappropriate for environments like clean rooms, food processing plants, or where it could contaminate products.
Right, wintergreen cookies probably aren't ideal.
Probably not. The warning signs themselves are incredibly detailed, far beyond a generic caution fire system notice. NFPA 12 mandates a comprehensive signage strategy.
Signage strategy. Sounds serious.
It is. Requiring conspicuous signs in every protected space, at every entrance to protected spaces, in nearby spaces where CO2 could migrate and create a hazard, outside CO2 storage rooms, and at all manual operation points.
Signs everywhere.
These signs must conform to ANSI Z535.2 in terms of format, color, lettering, and symbols, ensuring they are universally understandable. They typically use a 3-panel format with very specific wording.
Specific wording, okay. Like what?
For example, a sign in every protected space reads, "Warning, carbon dioxide gas can cause injury or death. When alarm operates, vacate immediately."
Clear and direct.
At every entrance to a protected space, it's, "Warning, carbon dioxide gas can cause injury or death. When alarm operates, do not enter until ventilated."
Don't go in. Wait for ventilation.
And at a manual actuation station, it reads, "Warning, carbon dioxide gas can cause injury or death. Actuation of this device causes carbon dioxide to discharge. Before actuating, be sure personnel are clear of the area."
Warning before you pull the handle. Makes sense.
What's particularly noteworthy is that existing signs, if they meet general requirements, are acceptable only if the facility has a comprehensive signage training program in place for all personnel with access to the protected space.
So training is key for the signs to work.
Absolutely. This underscores that signs are only effective if people understand what they mean and how to react.
Okay, signs, alarms, delays. What about rescue if someone doesn't get out?
Moving to rescue and training, the standard mandates provisions for the prompt discovery and rescue of unconscious persons. This isn't left to chance.
Need a plan.
It explicitly calls for trained personnel equipped with self-contained breathing apparatus, or SCBA, and proficient in artificial respiration.
Trained rescuers with air packs.
Furthermore, thorough instruction and drills are required for all personnel who are within or in the vicinity of these protected areas, including maintenance or construction staff,
Everyone needs drills.
to ensure they know the correct actions to take if the system operates, how to evacuate, and what to do if a colleague is affected. Finally, ventilation is critical.
Ventilation, right? Because it's heavier than air.
Exactly. Means for prompt and forced ventilation of hazardous areas must be provided, as carbon dioxide is heavier than air and can collect in low-lying spaces. Without active ventilation, dangerous pockets of CO2 could linger for extended periods, creating persistent risks even after the immediate fire threat has passed.
Got to clear it out properly. #tag evacuation procedures and lockout valves. Okay, we've mentioned lockout valves a couple of times now as a really critical safety feature.
Essential.
Let's delve deeper. What exactly is a lockout valve, and why is it so fundamentally important for protecting people?
This raises an important question. We've mentioned lockout valves a couple of times as a critical safety feature. Let's delve deeper into what that actually means and why it's so important for human safety. A lockout valve is a manually operated valve installed in the discharge pipe.
In the pipe itself.
specifically situated between the nozzles and the main CO2 supply. Crucially, it can be physically locked in the closed position, much like a padlock on a circuit breaker.
Like a safety padlock.
Exactly. This is an absolutely vital safety feature, specifically designed to prevent the flow of carbon dioxide to protected areas during maintenance, testing, or any time personnel are intentionally present.
So you lock it closed when people are inside.
Precisely. It's also mandated in any location where discharged CO2 could migrate and create a hazard in an adjacent area.
Ah, prevent leakage into other rooms.
Right. The practical implications are significant. During any maintenance or testing procedures on the system or within the protected space, the CO2 system must be locked out.
Must be.
Or the protected space and any potentially affected adjacent spaces where CO2 could migrate must be evacuated. This isn't a suggestion, it's a non-negotiable step to prevent accidental discharge.
No shortcuts.
If, however, fire protection needs to be maintained during this lockout period, perhaps due to a critical ongoing operation, then a fire watch must be assigned.
A fire watch. What's that?
This fire watch consists of personnel specifically equipped with suitable portable or semi-portable firefighting equipment and, crucially, a communication link to a constantly monitored location.
Okay, so trained people watching with extinguishers and radios.
Basically, yes. And of course, the authorities responsible for continuity of fire protection must be notified of both the lockout and its subsequent restoration. It's explicitly stated that a mere electrical service disconnect switch is not a substitute for a physical lockout valve.
Right, because the CO2 has its own pressure.
As the CO2 system operates under its own pressure independent of electrical power. This highlights the multi-layered approach to safety.
That makes perfect sense. It's about making absolutely sure that while the system protects against fire, it doesn't inadvertently harm the very people it's designed to protect. But once the fire is out, is that the end of it?
Not necessarily.
Why isn't just extinguishing the fire enough? Why is the duration of protection so important?
What's fascinating here is that simply knocking down the flames isn't always the complete solution, especially with deeper-seated or persistent ignition sources.
Smoldering fires.
Exactly. The standard emphasizes that an effective agent concentration must not only be achieved but maintained for a sufficient period. This duration serves two critical purposes. It allows for effective emergency action by trained personnel, and, most importantly, it prevents reignition.
The reignition risk.
If there's a persistent ignition source, such as an electrical arc, residual heat in equipment, a smoldering hotspot, or a deep-seated fire within solid combustibles, the fire can easily recur once the CO2 agent dissipates.
So the gas floats away and boom, it starts again.
Potentially, yes. The extended duration ensures that the fuel cools below its auto-ignition temperature, or that any hidden embers are fully suppressed, preventing a reflash. It's about ensuring the fire stays out.
That's a crucial detail. A fire isn't truly out until it's cool. And what about safety around electrical equipment? While CO2 is non-conductive, what are the specific rules regarding electrical clearances for the system components themselves?
Indeed, while CO2 itself won't conduct electricity, all system components, the piping, nozzles, detection devices, and wiring must maintain specific minimum clearances from live electrical parts.
Keep the pipes away from the live wires.
Essentially, yes. The standard provides a detailed table, Table 4.3.4.1, which outlines these requirements. For voltages up to 161 kVV, these clearances are derived from NFPA 70, the National Electrical Code,
The NEC.
which defines safe distances to prevent arcing. For higher voltages, 230 kV and above, they reference Table 124 of ANSI C2, the National Electrical Safety Code, and in Canada, CSA C22.1.
Specific codes for different voltages.
Right. To give you a practical example, for a system component near live electrical parts operating at 161 kV, the minimum clearance required is 58 inches, or approximately 1,473 millimeters.
Almost 5 feet. That's quite a distance.
Yep, it is. This meticulous attention to detail ensures that the physical installation of the CO2 system does not inadvertently create a new electrical hazard, especially crucial in high-voltage environments.
Now that we truly understand the agent itself and its critical safety aspects, let's explore the different types of CO2 extinguishing systems.
The different ways it's applied.
The standard actually classifies them quite distinctly, each tailored for very specific fire hazards.
That's right. If we connect this to the bigger picture, these classifications truly demonstrate the versatility of CO2 as an extinguishing agent.
Okay.
The main types we'll discuss are total flooding systems, local application systems, hand hose line systems, standpipe systems with mobile supply, and specialized marine systems.
Lots of types.
Each is a precisely engineered solution designed to address particular fire scenarios and hazard configurations, ensuring the most effective and safe application possible. Hashtag tag tag total flooding systems, Chapter 5.
Okay, let's start with total flooding systems. When I hear that, my mind immediately jumps to a completely sealed room being entirely filled with gas. Is that a pretty accurate mental image?
That's precisely the concept. A total flooding system is designed to discharge carbon dioxide into and completely fill an enclosed space or an enclosure built around a specific hazard.
Fill the whole box.
To achieve a precise extinguishing concentration throughout the entire volume. This means the space needs to be reasonably well enclosed to minimize agent loss.
Yeah, keep the gas in.
Because if the gas leaks out too quickly, the concentration won't be maintained. Any unclosable openings, like small gaps around conduits or ventilation ducts, must be meticulously compensated for by adding a calculated amount of extra CO2 to ensure the target concentration is still met.
Account for leaks with extra gas.
Exactly. Ideally, larger openings, like doorways or windows, should be arranged to close automatically either before or simultaneously with the CO2 discharge.
Automatic door closers.
Similarly, forced air ventilation systems should preferably be shut down, or if they can't be, additional compensating gas must be provided. It's all about creating and maintaining that suffocating inert atmosphere until the fire is extinguished and cooled.
Makes sense. Shut down the fans, close the doors.
Now, the type of fire dictates the exact CO2 quantity needed. For surface fires,
Surface fires like liquids.
yes, those involving flammable liquids and gases like gasoline, propane, or even hydrogen, the quantity is based on average conditions, assuming prompt extinguishment.
Okay.
The standard provides theoretical minimum CO2 concentrations and then slightly higher design concentrations for a crucial safety margin.
Theoretical versus design. Safety factor built in.
Precisely. For example, for gasoline, the theoretical minimum concentration for extinguishment is 28% CO2, but the design concentration is specified at 34% to provide that safety buffer.
28 theoretical, 34 design for gas.
Right. For highly flammable hydrogen, it's 62% theoretical, and the design concentration jumps to 75%.
Wow, 75% for hydrogen. Needs a lot more.
It does. The quantity also depends on the volume of the space, using what are called volume factors. For small spaces up to 140 cubic feet, you'd use 14 cubic feet per pound of CO2, while for much larger spaces over 50,000 cubic feet, it's 22 cubic feet per pound.
So the factor changes with size.
And if the design concentration is higher than 34%, additional material conversion factors are also applied to ensure accuracy.
More calculations for higher concentrations.
Okay, what about deeper fires?
Now, for deep-seated fires, which involve solid combustibles like paper, wood, or textiles, the requirements change significantly.
Things that smolder inside.
Exactly. These fires smolder deeply, requiring the extinguishing concentration to be maintained for an extended period, typically a minimum of 20 minutes.
20 minutes minimum whole time.
Because the CO2 needs to penetrate deep into the material to cool and smother those hidden embers. The quantity here is based on fairly tight enclosures, and specifically accounts for thermal insulating effects, using specific flooding factors.
Need more gas for longer, basically. Yes. What's fascinating here is the design dilemma. Sometimes a system designed for surface fires might be chosen due to initial cost.
Cheaper option.
But if a deep-seated fire develops, there's a significant risk of reflash once the initial agent dissipates because it hasn't cooled the core.
Save money upfront, risk reignition later.
It's a critical decision that weighs initial cost against the ultimate level of protection against all potential fire types.
Are there other conditions that affect the CO2 quantity, like temperature?
Yes, the standard also meticulously accounts for special conditions. If an enclosure is normally above 200 degrees F, 93 degrees C, an additional 1% of CO2 quantity is required for each additional 5 degrees F, 2.8 degrees, above that baseline.
More CO2 needed for hotter rooms.
Right. This compensates for the higher ambient temperature, which means the fire is already hotter and the CO2 might dissipate faster, requiring more agent to achieve effective cooling and suppression.
Makes sense. What about ventilation you can't shut off?
If ventilating systems cannot be shut down during discharge, a challenging scenario, additional CO2 must be added.
More gas again.
This extra amount is calculated by determining the volume of air moved by the ventilation system during the liquid discharge period, dividing that by the flooding factor, and potentially multiplying by a material conversion factor if the design concentration is above 34%.
Complex calculation for leaky rooms.
It is. It's a complex calculation to ensure the agent isn't simply blown away before it can do its job.
So when you're pumping all that CO2 into a sealed or semi-sealed room,
Mm.
what actually happens to the air and the pressure inside?
Good question.
Does it just get pushed out, or does the pressure build up to dangerous levels? What considerations are there for that venting aspect?
That's a critical element that designers must consider. When CO2 rapidly expands from a liquid to a gas, it creates significant pressure.
Pressure buildup.
Without adequate venting, this pressure could compromise the structural integrity of the enclosure itself. Furthermore, the rapid influx of CO2 displaces not just oxygen, but also any flammable vapors, and these need a safe way to escape.
Gotta let the pressure and bad fumes out.
Exactly. For very tight enclosures, the standard provides specific equations to calculate the necessary free venting area. For example, in U.S. customary units, the formula is X equals Q 1.3 lip-P.
Okay, where X is the required free venting area in square inches, Q is the calculated CO2 flow rate in pounds per minute, and P is the maximum allowable strength of the enclosure in pounds per square foot.
So flow rate versus room strength.
Right. This calculation assumes that CO2 expands to approximately 9 cubic feet per pound, 0.56 millipilograms. Without adequate venting, the pressure could not only damage the enclosure but also hinder the uniform distribution of the extinguishing agent, leading to an ineffective suppression.
So venting is crucial for the room and for the system to work.
Absolutely critical. #tag local application systems chapter 6.
Not every fire, as we know, is conveniently contained within a sealed box. What about hazards that are out in the open, like a large manufacturing machine, a dip tank, or a specialized piece of equipment?
Right, the non-enclosed hazards.
How do CO2 systems handle those? This is where local application systems come into play, and what's fascinating here is how they differ fundamentally from total flooding.
How so?
Instead of filling an entire space, a local application system consists of a fixed supply of CO2 discharged directly onto the burning material.
Direct application, like aiming a nozzle.
Exactly. It's used precisely where the hazard is not enclosed or where the enclosure doesn't meet the requirements for total flooding. Their primary use is for the extinguishment of surface fires in flammable liquids, gases, and shallow solids, such as in dip tanks, quench tanks, or rolling mills found in many industrial processes.
Specific industrial uses.
It's a surgical strike rather than an area saturation.
Okay. What are the rules for setting these up?
For hazard specifications, the standard mandates that the entire hazard must be protected. This isn't just the visible fire, but includes all areas that could become coated by combustible liquids or shallow solid coatings,
Cover everything that could burn.
encompassing areas subject to spillage, leakage, dripping, splashing, or even condensation. This also extends to associated equipment like drain boards, hoods, and ducts that could potentially extend the fire.
Think about where it could spread.
Right. A critical environmental consideration for local application systems is that wind and strong air currents must not impair the protection.
Wind could blow the CO2 away.
Precisely. If there's significant airflow, the CO2 agent could be dispersed before it can effectively cool and smother the flames, making the system useless. This might require baffles or other physical barriers to ensure the agent stays concentrated over the hazard.
Might need walls or shields. How much CO2 do these need? Is it different from total flood?
Yes, the quantity requirements are different. For CO2 quantity requirements in local application systems, the amount is based on the total discharge rate needed to blanket the hazard area or volume and the specific time required for extinguishment.
Rate and time.
When high-pressure storage is used, that is, cylinders at ambient temperature, the computed CO2 quantity must be increased by 40% to determine the nominal cylinder storage capacity.
40% extra for high pressure. Why so much?
This 40% increase isn't just a buffer, it's a stark reminder of the physics at play. A significant portion of the initial CO2 blast from a high-pressure cylinder effectively vaporizes and becomes gas almost immediately as pressure drops before reaching the target.
A lot flashes to gas right away and doesn't make it as liquid.
Exactly. This underscores the engineering challenge of delivering the critical liquid agent efficiently in these systems. Furthermore, extra CO2 is needed to compensate for any liquid that vaporizes in cooling the piping,
Gas loss cooling the pipes.
which can be significant in long runs, especially in colder environments. While listing tests for nozzles might be as short as 20 seconds, the minimum discharge duration specified in the standard is 30 seconds.
30 seconds minimum discharge.
Providing a crucial safety factor to ensure sustained suppression. For hot surfaces like cooking oils, even longer discharge times are necessary to cool the fuel below its auto-ignition temperature to prevent reignition,
Longer time needed for hot stuff like oil.
making the cooling aspect just as vital as the smothering.
How do they design these? How do they figure out the nozzles and rates?
The standard outlines two main methods for system design under local application, each suited to different hazard geometries. The first is the rate-by-area method.
Rate by area. For flat things.
Primarily, yes. This is used for flat surfaces or low-level objects associated with horizontal surfaces, such as the surface of a dip tank. The design must be based on listing or approval data for individual nozzles.
Use tested nozzle data.
And extrapolation outside these limits is not permitted. You can't just guess how a nozzle will perform in a new configuration. Nozzle discharge rates are precisely determined by their location and projection distance.
Depends on where the nozzle is.
For instance, overhead nozzles are rated by their maximum distance from the surface, while tank-side nozzles are rated by the throw required to cover the surface. The maximum area protected by each nozzle is also determined by its listing.
Listed coverage area per nozzle.
What's interesting is that the area per nozzle can be increased up to 40% for certain coated surfaces, provided they are designed for effective drainage, and liquid pools don't exceed 10% of the protected area.
Can cover more area sometimes with conditions.
Or up to 20% for openings if specific conditions are met, allowing for some flexibility in complex industrial setups. Nozzles must be free of obstructions and strategically located to cover any coated stock extending above a protected surface, like 2 feet beyond.
Keep nozzles clear. Aim carefully. What's the other method?
The second method is the rate-by-volume method.
Rate by volume for 3D shapes.
Exactly. This is specifically employed for three-dimensional irregular objects that cannot be easily reduced to equivalent surface areas. Think of a complex piece of machinery with many nooks, crannies, and interlocking parts.
Like a big engine or something.
Right. In this method, the total discharge rate is based on the volume of an assumed enclosure that entirely surrounds the hazard, essentially creating a virtual enclosed space for the calculation.
Draw an imaginary box around it and calculate for that volume.
Precisely. This allows for effective protection of complex machinery or equipment that doesn't fit neatly into the flat surface model, providing a design framework for challenging geometries. Hashtag hand hose line systems, Chapter 7.
Now, what about those situations where you need a more hands-on approach? I'm thinking about scenarios where a large fixed system might not be practical, but you still need rapid, direct fire suppression.
Exactly. This is where hand hose line systems come in. They consist of a hose and nozzle assembly connected either to fixed piping or directly to a CO2 supply.
Like a CO2 fire hose.
Essentially, yes. It's crucial to understand that these are not a substitute for fixed extinguishing systems in most cases.
Not a replacement for automatic systems.
Right. They are primarily used in very specific scenarios where the hazard is either inaccessible to fixed protection, perhaps a constantly moving target, or an irregularly shaped area, or consists of scattered individual hazards that cannot be economically or adequately protected by fixed nozzles.
For tricky or spread out hazards.
The authority having jurisdiction, or AHJ, ultimately makes that determination, often balancing practicality with the utmost safety.
AHJ decides. Okay, since someone has to operate it, training must be huge.
Because the operation of hand hose lines relies heavily on the individual ability and technique of the operator, training is absolutely vital. This isn't a passive system.
Needs skilled operators.
Personnel who are likely to use this equipment must be thoroughly trained in its operation and the applicable firefighting techniques, understanding both the power and the hazards of CO2.
Gotta know how to use it safely and effectively. How much CO2 do these need?
Regarding CO2 requirements, the quantity stored must be sufficient to permit at least 1 minute of continuous use per hose line.
1 minute of spray time.
The standard also makes provisions for inexperienced personnel, acknowledging that the actual users might not be expert firefighters, so the supply needs to be robust enough for them to be effective under stress.
Assume non-experts might use it, so give them enough agent.
Right. If simultaneous use of multiple hose lines is possible, enough CO2 must be available to support all likely simultaneous operations for at least 1 minute. This ensures that even in a multi-pronged attack, the agent supply won't run out prematurely.
Enough for multiple hoses if needed. What about the hoses and nozzles themselves?
In terms of equipment specifications, the hose lines themselves must be built to withstand extremely high pressures. A minimum bursting pressure of 5,000 psi, 34,474 kPa for high-pressure systems.
5,000 psi. That's immense pressure.
And 1,800 psi, 12,411 kPa for low-pressure systems. To put that in perspective, a typical car tire is around 30-35 psi, so these hoses are engineered for immense force.
Seriously strong hoses.
The nozzle assembly must be easily handled by a single operator, featuring a quick opening shutoff valve to control the CO2 flow and a handle for directing the discharge.
Easy to use nozzle.
The hose must be coiled on a reel or rack, ready for immediate use without needing to be coupled, ensuring precious seconds aren't lost.
Ready to go instantly.
Critically, the controls for actuating the system should be located in the immediate vicinity of the hose reel, and the CO2 supply should be as close as possible to ensure rapid liquid discharge.
Controls nearby, supply close.
And an important safety point. Pressure should not remain in the hose line when it's not in use, preventing accidental discharge or hose degradation over time.
Don't leave the hose pressurized. Got it.
Yeah.
Hashtag standpipe systems and mobile supply. Chapter 8.
When I think of a standpipe system, I typically picture a fire department connecting their hoses to a building's water system.
A standard fire department connection, yeah.
Is there a CO2 equivalent of that, where a mobile supply can be brought in and quickly connected for fire suppression? That's a great analogy, and yes, there absolutely is. A standpipe system, in the context of CO2 suppression, is a fixed piping network, whether it supports total flooding, local application, or hand hose lines. But critically, it's without a permanently connected CO2 supply.
Pipes are there, but no CO2 tank connected.
Exactly. Instead, a mobile CO2 supply, typically mounted on a vehicle like a specialized fire truck, is quickly moved into position and coupled to the standpipe system.
CO2 truck hooks up to the building pipe.
Right. This approach offers incredible versatility. It can supplement existing fixed systems, protect specific hazards on its own, or even serve as a readily available reserve supply for multiple hazards across a large industrial site.
Flexible option for large sites.
It's essentially a portable, high-capacity CO2 supply that can be rapidly deployed.
Who operates these? Fire department.
Because the mobile supply is primarily considered fire brigade or fire department equipment, its effective use relies heavily on trained personnel who understand its operation and the specific hazards it protects.
Trained responders needed.
Given that there might be inherent delays in getting the mobile supply to the hazard and making the necessary connections, the standard acknowledges that extra CO2 might be needed to compensate for those deployment times.
Need more gas to make up for the setup time.
Ensuring the required extinguishing concentration and duration of protection can still be met despite the operational lead time. Quick change couplings are absolutely essential to facilitate rapid and secure connection of the mobile supply to the fixed standpipe system, minimizing any delays during an emergency.
Quick connections are key. Hashtag marine systems. Chapter 9. Living here, close to the ocean, I can't help but wonder about fires on the high seas. Are there special considerations, modifications, and challenges for marine environments like ships, barges, or offshore platforms that NFPA 12 specifically addresses?
What's fascinating here is that marine installations, such as those on ships, barges, or offshore platforms, present some profoundly unique challenges that demand specialized fire protection.
Yeah, stuck out at sea is different.
Chapter 9 of NFPA 12 specifically outlines necessary modifications for these environments, though all other general requirements of the standard still apply unless explicitly modified by this chapter.
Chapter 9 for marine. Got it.
This highlights how specialized fire protection needs to be when you're dealing with confined spaces, potentially rough seas, and limited evacuation options.
Unique risks. What are some key differences?
A key actuation difference in marine systems relates to the size of the protected space. For very large spaces, automatic release of CO2 is not permitted for areas greater than 6,000 cubic feet, 170 meter mounds.
No auto-release in big ship spaces. Why?
Likely due to the large number of personnel potentially involved or the complexity of ensuring evacuation from such large, compartmentalized areas on a vessel. However, automatic release is permitted for spaces of 6,000 cubic feet or less, provided several stringent conditions are met.
Okay, smaller spaces can be automatic if.
There must be horizontal egress to an open deck, meaning a clear path directly outside. The enclosure must be unmanned during operation, the system must be locked out when personnel are present, and crucially, the automatic actuation cannot interfere with the safe navigation of the vessel.
Strict rules. Path out, unmanned, locked out, doesn't affect steering.
Exactly. This carefully balances the need for rapid fire suppression with the unique life safety and operational demands of a marine vessel, where human presence and the ability to control the ship are paramount.
How about manual operation on ships?
For manual operation in marine systems, there are also very specific requirements designed to prevent accidental discharge while ensuring availability in an emergency. Generally, two separate valves are required for releasing CO2 into any protected space.
Two valves for manual release.
Yes, one to control discharge from the CO2 storage cylinders, and a second to control discharge into the specific protected space. This dual valve system adds an extra layer of safety, requiring two distinct actions to release the agent.
Two actions needed, less chance of mistakes.
An exception exists for smaller systems, those with 300 pounds, 136 kilograms of CO2 storage or less, where only one valve is needed if the space is normally unoccupied and has horizontal egress.
Small systems, unoccupied, easy exit, one valve. Okay.
Separate manually operated controls must be provided for each valve, and one set of these controls must be located outside at least one main means of egress from each protected space, ensuring accessibility during an emergency.
Controls outside the space.
In addition to these normal manual controls, emergency manual controls are also required for each valve. These controls are typically located inside a clearly identified release box, and if the box is locked, a key must be provided in a break glass enclosure conspicuously located adjacent to it.
Emergency controls in a break glass box.
Emphasizing immediate access when needed.
What about the alarms on ships?
Marine alarms also have a critical difference from land-based systems. The audible pre-discharge alarms and time delays, which must be a minimum of 20 seconds, must depend only on CO2 pressure as their power source, not external electricity.
Alarms powered by the CO2 pressure itself.
Yes. This is a vital design choice, ensuring they function even if the vessel experiences a complete loss of electrical power during an emergency, maintaining a critical life safety function when all else might fail.
Power goes out, alarms still work. That's smart. Can you give examples of marine designs?
Sure. Let's look at some system design examples for marine applications to see how these principles are applied. For machinery spaces, which are often high-risk areas.
Engine rooms.
Right. The system is designed to achieve a 34% CO2 concentration based on the gross volume, with 85% of this concentration attained within a rapid 2 minutes.
34% in 2 minutes for engine rooms.
For cargo spaces, excluding vehicle spaces, the design is based on 1 pound of CO2 per 30 cubic feet of gross volume. The initial discharge quantity is calculated based on the net volume, accounting for the cargo itself.
Net volume, okay.
And critically, additional CO2 must be released as needed to maintain fire suppression, because fires in cargo spaces might not be fully extinguished by the initial discharge and could require intermittent releases until the vessel reaches port.
Cargo fires might need multiple shots of CO2.
Exactly. Clear instructions for this complex release procedure must be prominently posted. Vehicle spaces, on the other hand, require a higher 65% CO2 concentration maintained for 20 minutes, with 2/3 of that concentration achieved within 10 minutes.
Higher concentration, longer hold for vehicle decks.
And electrical equipment spaces on marine vessels are generally treated as dry electrical hazards, following the total flooding guidelines in Chapter 5.
Electrical spaces follow normal rules. What about testing on ships?
Inspection and maintenance in marine systems also have specific, rigorous provisions due to the harsh environment. Prior to any testing or maintenance of a fixed CO2 system, all personnel must be evacuated from the protected space, no exceptions.
So everyone out before testing.
Pressure tests of the piping must be performed using a dry, non-corrosive gas like nitrogen or CO2, increasing pressure in 50 psi increments. For high-pressure systems with stop valves, piping from the supply to the stop valves must withstand a minimum of 1,000 psi, 6,895 ksi, with less than a 10% pressure drop over 2 minutes.
Strict pressure testing.
And piping between stop valves and nozzles must withstand 600 psi, 437 kkPa, with similar leakage limits. For low-pressure systems, normally pressurized piping is tested at 300 psi, 2068 kPa, with no leakage permitted. This rigorous testing ensures the system's integrity and reliability in the demanding marine environment, where system failure could have catastrophic consequences.
Got to be sure it works reliably at sea. It's abundantly clear that these systems are incredibly complex, extending far beyond simply knowing what CO2 does.
Way beyond.
There's intricate engineering at every single component, every pipe, every valve. What goes into making these systems reliable?
That's right. If we connect this to the bigger picture, the sheer reliability and safety of these systems truly hinge on the meticulous design and installation of their individual components, and then crucially on rigorous ongoing inspection and maintenance.
Design, install, maintain. The whole life cycle.
It's a testament to the fact that even the smallest detail can have massive implications for fire safety and, above all, life protection. It's the constant attention to these nuts and bolts that transforms a powerful agent into a trusted protector. #tag detection, actuation, and control. Revisit Chapter 4.
Okay, let's talk about how these things actually get triggered. Detection, actuation, control.
The brains of the operation. Let's start with how these systems are classified in terms of operation. We have automatic operation,
Does it by itself?
which means no human action is required. The system detects a fire and triggers itself. Then there's normal manual operation,
Someone pulls a handle.
which involves human action through an easily accessible device, usually requiring just one control to activate the full system. Finally, emergency manual operation provides a fully mechanical means of actuation,
It's mechanical backup.
often system pressure assisted, located at or near the device being controlled. This is designed as a crucial backup in case automatic or normal manual systems fail, ensuring that in a true emergency, the system can still be deployed.
3 ways to trigger it. How does automatic detection work?
For automatic detection, systems rely on listed or approved methods capable of detecting heat, flame, smoke, combustible vapors, or other abnormal conditions indicative of fire.
Standard fire detectors.
Yes, but what's a crucial insight here is that simply using detectors at their maximum spacing, as they might be listed for general fire alarm use, can lead to excessive delay in agent release for a suppression system.
Oh, need detectors closer together for suppression.
Right. Suppression requires a much faster, more precise response than a general alarm. The actuation sequence for automatic systems is also very precise.
The sequence of events.
They sustain fire alarm signal, first activates pre-discharge alarms, which then trigger electrically operated pre-discharge time delays and more electrically operated pre-discharge alarms before finally actuating the CO2 releasing devices.
Alarm, delay, alarm again, then release. Very deliberate.
This staged sequence isn't just about complexity, it's a vital part of personnel safety, ensuring a clear warning and time for evacuation before discharge.
Safety sequence? What about the devices themselves? Valves, controls.
The operating devices themselves, including CO2 releasing devices, discharge controls, and equipment shutdown mechanisms, are all considered integral to the system's successful performance. They are designed to function reliably within a wide temperature range, typically from -20 degrees C, 129 degrees C to 66 degrees.
Wide temperature range.
And must be protected from mechanical, chemical, or other damage. Crucially, any devices with manufacturer-specific connections used to control CO2 release must have distinctive or distinctively marked connections to prevent improper installation.
Make sure you can't hook it up wrong.
Because even a minor misconnection could lead to system failure. For manual controls, there are specific ergonomic requirements. They must not require a pull force of more than 40 pounds, 178,
Not too hard to pull.
or a movement of more than 14 inches, 356 millimeter, ensuring they can be operated quickly and effectively in an emergency. And at least one manual control must be positioned no more than 4 feet, 1.2 meters above the floor for easy access by most adults.
Easy to reach, easy to operate. You mentioned equipment shutdown.
An absolutely crucial aspect is equipment shutdown. If the continuing operation of equipment associated with a hazard could sustain the fire, for example, a fuel pump feeding flammable liquid to a burning area, its power or fuel sources must be automatically shut off as an integral part of the system's operation.
Cut the fuel. Cut the power to the burning thing.
Exactly. This prevents the fire from being continuously fed, giving the CO2 the best chance to extinguish it. The only exception noted is for lubricating oil systems associated with very large rotating equipment, like massive turbines.
Steam turbines are different.
In these cases, an extended CO2 discharge is provided to cool the equipment down gradually over time, as a rapid, abrupt shutdown could potentially be more damaging to the machinery than helpful in the fire scenario.
Gentle shutdown for big machines. How do you know the system is working or if there's a problem?
Finally, supervision is a core element for reliability. Automatic systems and lockout valves are typically supervised, meaning their operational status is constantly monitored.
Monitored electronically.
Usually, yes. Any interconnections critical for the system's control and life safety, such as wiring to alarms or shutdown devices, must also be supervised. If an open circuit, a ground fault condition, or a loss of integrity in pneumatic control lines occurs, anything that would impair full system operation, it must result in a distinct trouble signal at a central monitoring panel.
Trouble signal if anything's wrong.
This ensures that any fault is promptly identified and addressed, maintaining the system's constant readiness. Think of it like a car's dashboard warning lights, but for a fire suppression system where lives and critical assets are at stake.
Critical warning system. Hashtag carbon dioxide supply.
Yeah.
Revisit Chapter 4. So we've got the controls, the detection, the intricate sequences, but what about the CO2 itself? How much do we need, and how is it actually stored for these powerful systems?
What's fascinating here is the careful consideration given to the carbon dioxide supply, which directly impacts the system's effectiveness. The main supply must be sufficient for the largest single hazard protected,
Enough for the biggest risk.
or for a group of hazards that are designed to be protected simultaneously. If continuous protection is required, meaning the hazard needs to be protected even after an initial discharge, perhaps for a potential reflash, a reserve supply is also mandated.
Main supply and a backup reserve.
Right. This reserve is often permanently connected and arranged for easy changeover, or sometimes an unconnected reserve is approved by the AHJ if it can be deployed rapidly. The required quantity also rigorously considers the time needed to replenish the system after a discharge, so it's not left vulnerable.
Plan for refills. How's it stored? Big tanks. Cylinders.
Storage containers vary significantly depending on the system design and the specific needs of the hazard. High-pressure cylinders are rechargeable, storing liquid CO2 at ambient temperatures.
High-pressure cylinders like welding gas.
Similar concept, yes, which means the internal pressure fluctuates with the surrounding temperature. For example, it's around 850 psi, 500 and 860 kPa, at 70 degrees F, 21 degrees C.
Pressure changes with temperature.
These cylinders must meet stringent U.S. DOT or Canadian Transport Commission requirements, reflecting the dangers of storing high-pressure gas. They undergo hydrostatic testing every 5 years to ensure integrity.
Regular pressure tests.
Or, if continuously in service without discharge, they can go up to 12 years from the last test before being discharged and retested. Each cylinder is fitted with a rupture disc pressure relief device for safety,
Safety disc to prevent explosion.
preventing catastrophic failure if pressure builds excessively. When manifolded into a bank, cylinders are supported in racks for easy servicing and weighing, with automatic mechanisms to prevent CO2 loss if a cylinder is removed for maintenance.
Banks of cylinders on racks.
Ambient storage temperatures for high-pressure systems must be carefully managed. 32 COSH 120 degrees BAF, 0 MOS 49 degrees C for local application, and 0 NAF 130 degrees C for total flooding,
Keep them within a temperature range.
with external heating or cooling allowed if the ambient conditions fall outside this range. This is crucial because temperature directly impacts the pressure and thus the discharge rate.
Temperature affects performance. What's the other storage method?
In contrast, low-pressure storage containers are designed to maintain the CO2 at a nominal 300 psi, 2068 kPa, which corresponds to a precisely controlled low temperature of approximately 0 degrees F, negative 18 degrees C.
Low pressure, but super cold storage, like a giant freezer tank.
Essentially, yes. These are welded pressure vessels, much like large insulated thermos flasks, equipped with automatically controlled refrigeration or heating systems to maintain that precise temperature and pressure.
Refrigerated tanks.
They feature a liquid level gauge, a pressure gauge, and a high-low pressure supervisory alarm set to trigger if the pressure goes above 90% of the maximum allowable working pressure or below 250 psi, 1724 kPa.
Alarms for pressure and level.
This constant monitoring ensures the system is always ready and at optimal performance. The filling density for these units can range from 90–95%, maximizing storage efficiency.
Fill them almost full.
If you look at a low-pressure unit, what stands out is its appearance. It's typically a large insulated vessel with an external refrigeration unit, visually very different from a bank of high-pressure cylinders.
It looks like a big insulated tank with a fridge unit attached.
Exactly. This active temperature control ensures a consistent flow rate regardless of ambient conditions, making it ideal for very large-scale systems requiring a prolonged, stable discharge.
Consistent flow, good for big systems. Hashtag distribution systems. Revisit Chapter 4. So we've got the CO2 and how it's stored under either high or carefully controlled low pressure. Now, how does it actually get from those storage containers to the fire?
The delivery system.
This involves the distribution system, and I imagine the piping and nozzles have to be incredibly robust to handle such extreme conditions.
Absolutely. The distribution system is where the incredible pressures and extreme cold of CO2 are managed, moving the agent from storage to the point of discharge. The piping must be made of metallic, non-combustible material,
Metal pipes, obviously.
capable of predictable performance under immense stress and cryogenic temperatures. Common materials include black or galvanized steel, like ASTM A53 or A106 with their specific steel pipe standards, or stainless steel, TP304 or TP316.
Specific types of steel.
Critically, Class 150 and ordinary cast iron pipe are not permitted.
No cast iron. Why not?
Because they lack the necessary strength and ductility to handle the extreme pressures and thermal shock of CO2 discharge without bursting.
Too brittle for the pressure and cold.
Exactly. Minimum pipe schedules are rigorously specified. For high-pressure systems, pipes ranging from 1-inch to 4-inch diameter must be a minimum of Schedule 80.
Schedule 80 pipe. That's thick-walled pipe.
It is. This isn't just a random specification. Schedule 80 pipe has a significantly thicker wall than standard pipe, which is crucial for withstanding the immense sudden pressures and cryogenic temperatures of a CO2 discharge without bursting.
Dirt traps.
Consisting of a T with a cap nipple at least 2 inches long, are required at the end of each pipe run to prevent blockages, acting as a last-line defense filter.
Catch debris before the nozzle.
Catching any tiny debris before it can clog a crucial nozzle, because even a speck could compromise the system when lives are on the line.
Good idea. What about the pipe fittings?
Moving to fittings, Class 150 and cast iron fittings are again explicitly not permitted for the same reasons as the pipe. Instead, malleable iron, forged steel, or stainless steel fittings are required.
Stronger fittings needed too.
Specifically designed to withstand the system pressures. For high-pressure systems, Class 300 malleable iron fittings are typically used for smaller sizes, with forged steel for larger pipes, and flanged joints upstream of stop valves, typically Class 600, indicating their pressure rating.
Specific classes based on pressure and valves.
For valves, they must be listed or approved and capable of withstanding the expected pressures, such as an 1800 psi, 12,411 kPa, hydrostatic test for low-pressure systems. They also must be protected from mechanical damage, as a compromised valve means a compromised system.
Listed, tested, protected valves. Now the nozzles, that's where the CO2 actually sprays out.
The discharge nozzles are equally critical. They must be listed or approved for their specific discharge characteristics, meaning they've been tested to prove they deliver the CO2 effectively.
Tested performance.
They are constructed with corrosion-resistant orifices and are strong enough for the intense working pressures and temperatures. What's fascinating here is that each nozzle must be permanently marked with its equivalent single orifice diameter.
Marked with an equivalent size.
Yes, regardless of the actual shape or number of orifices it has. For example, a No-4 nozzle indicates an equivalent 432-inch diameter orifice.
Standardization for calculations.
Exactly. This standardization ensures that during design and installation, engineers can precisely calculate flow rates and coverage, even with complex nozzle designs. If clogging is a risk, nozzles must be equipped with frangible discs or blowout caps that will rupture to clear any obstruction upon discharge.
Blowout caps if they might get clogged. How are flows calculated?
For flow calculation, the design is based on average storage pressures 300 psi, 2068 kPa, for low-pressure systems, and 750 psi, 5171 kPa, for high-pressure systems at 70 degrees F.
Based on average pressure.
The design nozzle pressures must meet minimums, not less than 150 psi, 2064 kPa for low-pressure systems, and greater than or equal to 300 psi, 2068 kPa, for high-pressure systems.
Minimum pressure at the nozzle.
These minimums ensure sufficient force to propel the CO2 effectively into the hazard area. Finally, pipe hangers and supports must be designed and installed according to recognized industry practices.
You gotta hang the pipes properly.
Using steel components attached to rigid structures. They are specifically designed to prevent lateral movement during the high-force discharge. Imagine the sudden kick as a high-pressure gas rushes through, but allow longitudinal movement to accommodate thermal expansion and contraction as the pipes rapidly cool down.
Stop sideways movement, allow lengthwise movement for temperature changes?
Exactly. Rigid hangers are specifically required wherever there's a change in elevation or direction, providing crucial structural stability.
Rigid support at turns and drops. #tag inspection, maintenance, and instruction. Revisit Chapter 4. So we've talked about the meticulous design, the specialized components, and the powerful agent. But a system, no matter how well designed, is only as good as its upkeep.
Absolutely. Maintenance is key.
What are the nuts and bolts of inspecting, maintaining, and ensuring everyone knows how to operate these powerful systems over their lifetime?
This raises an important question. How do we ensure these silent protectors are always ready when that critical moment arrives? The standard details rigorous, multifaceted procedures. First, specifications and plans.
Plans and paperwork first.
must be prepared by qualified personnel and submitted to the authority having jurisdiction, AHJ, before any installation begins. These detailed plans must include comprehensive information on the hazard, precise CO2 quantities, exact nozzle and pipe locations, detection and control specifics.
Everything documented.
And if any changes occur during installation, as-built drawings must be meticulously prepared. The system owner is ultimately responsible for maintaining a comprehensive instruction and maintenance manual, which is the system's ongoing Bible.
Owner keeps the manual. What about approving the installation?
Next is approval of installations. Once the system is complete, it must be thoroughly inspected, tested, and documented by qualified personnel for AHJ approval, using only listed or approved equipment.
Inspected and tested by qualified people.
This includes a thorough visual inspection and rigorous operational tests. Critically, full discharge tests are highly recommended and rarely waived.
Actually firing the system off.
Yes, because factors like extra cost or interruptions to production are explicitly not considered valid reasons for waivers.
No excuses not to test it fully.
Right. These tests are comprehensive. They verify that all cylinders open, CO2 flows correctly from every nozzle, time delays, alarms, and interlocks function as intended. For total flooding, they confirm the target concentration is achieved and maintained for the required duration. For local application, they verify proper duration and coverage of the hazard. And for hand hose lines, they confirm liquid flow and pattern.
The ultimate proof it works. What about ongoing checks?
Then there's ongoing care. Inspections must be conducted at least every 30 days.
Monthly checks.
A quick visual check to assess operational condition. This includes verifying that all cylinders are in place and secured, checking normal pressure and valve status for low-pressure units, ensuring the CO2 storage is properly connected, that manual actuators and tamper seals are intact, nozzles are clear of obstructions, detectors are in place, and the control panel shows a normal ready condition.
Quick visual look over each month.
This regular visual check can catch minor issues before they become major problems.
And deeper maintenance.
Maintenance is required at least annually, going far beyond the monthly inspection.
Yearly maintenance.
This involves a more thorough verification of the system's operation, reviewing the hazard configuration, ensuring the size, type, openings, and fuels haven't changed in a way that compromises the design.
Check if the room or hazard changed.
And testing all time delays, alarms, both audible and visible, warning signs, and detectors. Discharge tests are performed, if advisable.
Test everything annually. How about the CO2 levels?
For container levels, high-pressure cylinders must be weighed every 6 months.
Weigh the cylinders twice a year.
And if there's a loss of more than 10% in net content, they must be refilled or replaced immediately. Low-pressure liquid levels are observed weekly.
Check low-pressure tanks weekly.
With refilling required if there's more than a 10% loss, unless the minimum gas requirements for protection are still met.
Keep the tanks topped up. What about the hoses?
Finally, hose testing is mandated every 5 years for all hand hose lines.
Test hoses every 5 years.
This involves a hydrostatic test at high pressures 2,500 psi, 17,239 kPa for high-pressure systems, and 900 psi, 6,205 kPa for low-pressure systems, where the hose is removed, filled with water, pressurized for a minute, and observed for distortion or leakage.
Pressure test with water.
Electrical continuity is also checked for hand lines. Hoses that pass are marked with the test date, while those that fail are destroyed and replaced.
Mark good hoses, destroy bad ones.
All this leads to the critical point, instruction. Personnel who inspect, test, maintain, or operate CO2 systems must be thoroughly trained for their specific functions.
Training, training, training.
This isn't just basic training. It's highly specialized, ensuring competence and safety throughout the system's entire life cycle, because even the best system is only as effective as the people who interact with it.
Gotta know what you're doing. That deep dive into the components and maintenance really brings home the complexity. To make this knowledge even more concrete, let's turn to some fascinating real-world examples directly from the standard itself.
The Annex B examples, yeah.
Annex B of NFPA 12 offers these incredible case studies that show how all these complex principles we've discussed are applied in practice, tailoring solutions for unique fire risks.
These examples truly demonstrate the specific challenges posed by diverse hazards and how the standard tailored solutions, often requiring a combination of system types and intricate safety measures.
Real-world problem solving.
They're a window into the nuanced thinking behind fire protection engineering, showing how theory translates into practical, life-saving solutions for specific industrial processes. Hashtag commercial industrial food processing, deep fat, hot oil cookers.
Let's start with something that seems deceptively simple, but in an industrial setting becomes a serious fire hazard. Deep fat cookers and large-scale food processing plants.
Industrial fryers, yeah.
It's far more complex than just a home kitchen fryer, isn't it?
Not at all simple. What's fascinating here is the unique challenge these cookers present. Cooking oil can easily reach its auto-ignition temperature before it boils away.
Catches fire before it boils.
Yes, meaning that even if an initial fire is extinguished, the superheated oil itself can cause a reignition.
Big reignition risk.
Add to that the high production operations, often involving fume exhaust systems above the cookers, which become an integral part of the overall fire hazard, drawing flames and hot gases upwards.
The exhaust hood is part of the hazard.
Exactly. The solution isn't just about putting out a flame, it's about managing extreme heat, reignition risks, and interconnected equipment.
How do they protect the vats themselves?
The solutions are quite specific and highly conditional. For vat protection under a movable hood, total flooding with CO2 is generally not permitted unless incredibly strict conditions are met.
Usually not allowed under movable hoods. Why?
Probably because raising the hood breaks the enclosure needed for total flooding. The conditions include ensuring the hood is never raised during cooking, an automatic shutoff of power or fuel to heating elements if the hood is raised, and a mechanical high-temperature limit switch.
Lots of interlocks and safety switches.
That operates at not more than 20% above the maximum normal oil operating temperature. This switch must then automatically shut off power, prevent electrical hood raising, and activate alarms. A crucial part of this is requiring the CO2 quantity and discharge duration to be sufficient to cool the oil at least 60 degrees air, 33.3 degrees Celsius, below its auto-ignition temperature.
Need enough CO2 to cool the oil way down.
And thermal detection must actuate the system at or below the auto-ignition temperature. This detailed cooling requirement is vital because, as we discussed, simply extinguishing the flame isn't enough if the oil is still hot enough to spontaneously reignite.
Got to prevent that reflash. What's the alternative?
Alternatively, if a hood is designed to be in the full-up position during operation, a local application system is typically used for vat protection, directly targeting the oil surface.
Local application if the hood stays up. What about other parts? Drain boards, exhausts.
Other associated hazards in such environments also require tailored protection. Drain boards, where hot oil might drip, are often covered by local application systems using the rate-by-area method.
Local app for the drain boards.
Fume exhaust and fume removal systems typically use total flooding, designed to a 65% CO2 concentration to smother fires quickly within the ducts.
Total flood for the ducts. High concentration.
External oil heaters and hydraulic oil systems, often found near these cookers, are also protected by local application systems, either rate by area or rate by volume, depending on their configuration.
Protect the heaters and hydraulics too. Shutdown is probably key here.
What's absolutely critical across all these elements is equipment shutdown. Power or fuel sources to heating elements must be automatically shut off when the system operates, and manual resetting is required before operations can resume.
Auto shutdown, manual restart.
This prevents the fire from being continuously fed and ensures personnel safety during the aftermath and cleanup. Hashtag newspaper printing and rotogravure presses.
From the fiery challenges of hot oil, let's shift to the fast-paced world of newspaper and rotogravure printing.
Printing presses, yeah. Another complex hazard?
This industry, with its complex machinery and flammable inks, also holds hidden fire risks. What are the specific challenges here, and how does CO2 tackle them?
What's fascinating here are the multiple intense layers of fire risk in printing operations. You have highly flammable solvents in the inks, ink-saturated paper, lubricants, and significant electrical hazards from the complex machinery.
Flammable inks, paper, oil, electricity, lots of fuel and ignition.
Right. The intense vibration of the presses is a constant factor that can loosen connections or create friction, and fire can spread incredibly rapidly from one press unit to the folders, or vice versa, due to the continuous paper web.
Vibration and fast fire spread.
Rotogravure presses, with their heated drying drums and even more volatile flammable inks, represent an even more severe hazard due to the high temperatures involved. It's a perfect storm of accelerants, ignition sources, and rapid sped potential.
Sounds dangerous. How are they protected?
The solutions are precisely tailored to this dynamic, high-speed environment. Systems often employ group protection, where the CO2 quantity is calculated for a rapid 30-second discharge,
Protect sections or groups of the press. Fast discharge.
with a reserve supply sufficient for any adjacent groups that might become involved. Automatic actuation is the norm, with auxiliary manual means provided.
Auto actuation is standard.
To counter the incredibly rapid fire spread, fast-acting detectors, such as rate of rise or rate-compensated heat detectors, are absolutely crucial.
Need detectors that react to fast temperature changes.
Exactly. These detect sudden temperature spikes rather than just reaching a fixed temperature, providing the immediate response needed to prevent uncontrolled spread across the press. A complete shutdown of presses, ventilation, pumps, and heat sources simultaneously with the system operation is absolutely essential
Shut everything down instantly.
to prevent fire sustenance and stop the flow of flammable materials. Audible alarms must sound loudly in the press room and any lower levels where CO2 could accumulate, giving personnel precious seconds to evacuate.
Loud alarms again.
Special attention must also be paid to mounting detection systems to withstand the intense vibration of the presses, ensuring they don't malfunction or become dislodged.
Vibration-proof mounting for detectors.
And ensuring nozzle location and alignment is maintained during routine press maintenance is critical. Even a slight shift could compromise the discharge pattern.
Keep nozzles aimed right during maintenance. #tag below raised floors. KG computer rooms. Finally, let's talk about something incredibly common in our digital age. Computer rooms and data centers, specifically the hidden spaces below raised floors.
Underfloor spaces, very common.
These house vital electronics and cabling, but also represent a unique fire hazard. What's the protocol there?
This raises an important question. How do we protect critical infrastructure that is often out of sight and the highly sensitive equipment it supports? Total flooding CO2 systems have been a common and effective method for protecting underfloor spaces in computer rooms and similar electronic facilities for decades.
Total flood under the floor? Makes sense, it's enclosed.
Right. The enclosed nature of these spaces, often filled with dense cabling, makes them ideal for total flooding, allowing the CO2 to reach every potential ignition point. However, there's a critical safety caveat here.
A safety catch.
An aha moment that underscores the human element. The standard mandates that if any service or maintenance is conducted in that underfloor space, whether it's installing new cables, performing diagnostics, or cleaning, the CO2 system must be locked out to prevent any accidental discharge while personnel are present.
Lockout required if anyone goes under the floor.
Absolutely. This isn't a suggestion. It is a non-negotiable safety measure to protect technicians from suffocation or severe frostbite in a confined gas-filled space. It highlights that even in highly automated systems, human interaction and safety remain paramount.
Protect the techs working down there. #tag outro. Wow. What truly stands out to you from today's deep dive into NFPA 12?
So much detail, really.
For me, it's clear that while carbon dioxide is undeniably a highly effective fire extinguishing agent, its application is a marvel of engineering, truly a testament to precision.
It really is precise.
It's a constant, meticulous balancing act between powerful, rapid suppression and incredibly stringent, detailed safety protocols, especially when it comes to protecting human life.
Indeed. We've seen how the NFPA 12 standard, through its detailed chapters and annexes, addresses everything from the fundamental chemical properties of CO2 to the paramount human element of safety.
Covers all the bases.
From the complexities of designing large industrial systems to the unique critical marine applications and even specific challenges like deep fat fryers or printing presses, it's all covered.
So comprehensive.
This document is truly a testament to the continuous evolution of safety science, constantly refined by experience, real-world data, and ongoing research, always striving for better protection.
Always getting better. So what does this all mean for you, the listener?
Yeah, the takeaway.
The next time you walk into a server room, a data center, or a large industrial facility, you might just be in a space protected by these silent, unseen guardians.
They're all around us.
Now, you know they're not just there by chance. They've been meticulously designed, installed, and maintained according to standards that prioritize both effective fire suppression and, above all, human life.
Decades of learning built in.
It's a powerful reminder that safety is a constant, evolving conversation built on layers of expertise and careful consideration.
And it raises an important question for you to consider. How many other silent protectors like these, governed by equally rigorous yet often unnoticed standards, are at work in the world around us?
Good question.
ensuring our safety every single day in ways we rarely think about until we take a deep dive like this.
Makes you think. That's all for this deep dive into NFPA 12. Stay curious, stay informed, and we'll catch you on the next deep dive.